11.6 Derivatives of products and quotients. Our goal for this section is to learn how to compute derivatives of products and quotients using the product rule and the quotient rule. So we're first going to look at the product rule. So if you have a function f of x that equals u of x times v of x, and if both u prime and v prime exist, then the derivative of f prime of x, is equal to this formula, u times v prime plus u prime times v. Example 1. We want to find the derivative using the product rule. So I have a product there, so I want to use this rule here. So I need to know what u is, what v is, and what their derivatives are. So I'm going to let u equal this first factor, namely 2x squared plus 2x minus 3, and v is going to equal the second factor over here, 3x minus 5. Then I need to take the derivatives of these. So u prime, the derivative of u, is equal to 4x plus 2. And v prime, the derivative of v, is equal to 3. Now that I have u, v, u prime, and v prime, I'm going to plug all those components into the formula. So this is u times v prime plus u prime times v. So we took the derivative, but we don't want to leave it like this. We want to simplify, clean this up a little bit. So you see how there's a 3 here? I'm going to distribute that through. And over here on the right, since I have a product, I'm going to FOIL that. So this is what I get if after I distribute the 3 through and I FOIL the term on the right. Now you notice that there are terms that can be combined. So we have 6x squared and 12x squared. We can put those together. And I have 6x, negative 20x, 6x. I can put those together. And negative 9 and negative 10 are also like terms, so I can put those together. So after I clean that up, this is what I get. So that's my derivative, 18x squared minus 8x minus 19. That's my answer. The quotient rule. So if you have a function f of x that equals u of x over v of x, or u of x divided by v of x, and if all indicate derivatives exist, so you can find the derivative of u and v, and if v does not equal 0, because we can't divide by 0, then the derivative of f prime of x, is given by this formula here. So in the numerator, it starts v times u prime minus u times v prime. And in the denominator, you have v squared. Example 2. Find the derivative using the quotient rule. So g of x is a quotient, so we have to use this rule here. So I need to know what u is and what v is. U is always the numerator, so it's going to be x plus 4. And v is always the denominator, so in this case it's going to be x squared plus x plus 1. Then I need to take the derivatives of those. So the derivative of u is u prime, and that equals 1. And the derivative of v is v prime, and that equals 2x plus 1. Now I have u, v, u prime, and v prime. I'm going to just plug all of those into the formula. So here it is. So this part here is v times u prime minus u times v prime, and this is all over v squared. So now that I've taken the derivative, now I want to clean this up. So over here, since I have a product, I'm going to FOIL that. So this is what I get. Now I have a negative that I want to distribute through. So I get this. Now I have like terms that I can collect. After I do that, this is my final answer. And there's nothing else that cancels or cleans up. So I'm going to leave it like that. Now the denominator, it's being squared, just leave it like that. Don't try to expand that or FOIL it. Just leave it in factored form. Note, sometimes rewriting the function first will make finding the derivative easier. Example 3, find the derivatives. Let's look at part A first. So right now it looks like a quotient. You have x cubed minus 5x squared in the numerator and 4 in the denominator. But 4 is a constant, so we can rewrite this. I'm going to kind of pull the 4 out to the side. So instead of dividing by 4, I'm going to multiply by 1/4. So I have 1/4 times x cubed minus 5x squared. So now I don't have to use the quotient rule to find the derivative because 1/4 is a scalar multiple or constant multiple. So I just take the derivative of this part right here, the x cubed minus 5x squared. So when I take the derivative, this is what I get. 1/4 stays there. 3x squared minus 10x, and then I'm done. That's the derivative. Part B. So y equals 2x plus 3 squared. So that's the same as 2x plus 3 times 2x plus 3. Now I rewrote it and I can use the product rule, but I could keep rewriting this if I want to by FOILing it and collecting like terms. That gives me 4x squared plus 12x plus 9. And now that I have terms, I can just find the derivative using the power rule. So I don't have to use the product rule even though it was a product initially. So the derivative of this, y prime equals 8x plus 12. And then I'm done. Part C, f of t. So right now I have a quotient and the numerator is a product. So it looks like I would have to use the quotient rule and the product rule. I'm going to see if I can rewrite this to make life a little bit easier for me. And I'm going to start by FOILing the numerator. So once I FOIL and collect like terms, this is what I get. So now I don't have to use the product rule. I still have to use the quotient rule though. So there's my quotient rule. So now I have to denote what u is and what v is. U is always the numerator, so t squared minus 4, and v is the denominator, so 3t plus 7. Then I need to take the derivatives of those to get u prime and v prime. U prime equals 2t, and v prime equals 3. Now that I have those, I'm going to plug those into the formula. There we are. So this is my v times u prime minus u times v prime over v squared. So I took the derivative, but now I'm going to clean this up. I'm going to take the 2t and distribute that through, and I'm going to take the 3 and distribute that through. So this is what I get after distribution, and then there are like terms that I can collect, namely the 6t squared and the negative 3t squared. So I get this, and then I'm going to leave it like that. And the denominator, 3t plus 7 squared, I'm going to keep it as it is. I'm not going to FOIL that. Average cost. If the total cost of manufacturing X items is given by C of X, then the average cost per item is given by this formula here. We denote average cost with a bar over the C. It's like C bar of X. And it is given by our cost function, C of X divided by X. The marginal average cost is the derivative of the average cost function. So C bar is the average cost function, the marginal average cost, just C bar prime of X. And this is done in the same manner for revenue and profit. So example 4, the cost in dollars of selling X 100 pretzels in a month can be approximated by that cost function. So we want to answer parts A through D. So for A, we want to find the average cost function. So that's my formula for average cost. So I'm going to take my cost function, 80x plus 400, and divide it by x. So that's the average cost function. But I could clean this up a little bit if I wanted to. I'm going to take each term in the numerator, the 80x and the 400, and divide them by x separately. And then I can clean that up a little bit. So that's my average cost function. B, I want to find the average cost when 1,000 pretzels are sold. Now, remember that x is measured in hundredths. So I have to use x equals 10 for 1,000 pretzels. So I plug, there's my average cost function, and then I plug 10 into the average cost function. And I get 120. So the average cost at sales levels of 1,000 pretzels is $120 per 100 pretzels. C, find the marginal average cost function. So every time I see the word marginal, I think derivative. So there's my average cost, and then I'm going to rewrite it because I want to be able to use the power rule on this x here, and it cannot be in the denominator if I'm going to use the power rule. So I'm going to bring it into the numerator and write it as a negative exponent. Then I'm going to take the derivative. That's the derivative there. So that's the marginal average cost function. If I want to rewrite it, I can by putting x back into the denominator and making the exponent positive. D, find the marginal average cost when 1,000 pretzels are sold. So again, reminder, x is measured in hundredths, so I use x equals 10 for 1,000 pretzels. This was my marginal average cost function, and then I plug in 10, and I get negative 4. Negative 4. So at sales levels of 1,000 pretzels, if an additional 100 pretzels are sold, the average cost decreases by approximately $4 per 100 pretzels. So the negative means that the average cost is decreasing. And that's it for this section.